Hi gentlemen, this is a quick video to help go over our first BAM assignment, one dealing with periodic motion. The first couple problems for the B assignment talk about a pendulum, which is just something swinging back and forth. This pen could be a pendulum. All right. The first example talks about a grandfather clock and says that we use pendulums. The first place we used pendulums was really to keep track of time. Think about the size of a grandfather clock. It's about the size of a person, so it would make sense to have a pendulum that's somewhere smaller than me, but not this big. You wouldn't make a clock the size of me just to hold a little tiny pendulum. But before we do that, think about what would be convenient for a pendulum and a clock to keep track of. What would be a really useful time? We call this time, something periodic, it's period. So if you can think of a convenient period, like a second or two or a minute, you can try a few to see what comes out with a relatively normal length for a grandfather clock. In the second problem, we reference the Folcroft pendulum in the Franklin Institute. This is an 85-foot long pendulum. It's huge. If you haven't seen it, you should get down there and check it out. And we do the same thing. If you can tell me that Christian Huygens' formula about a pendulum's period is correct from the 1650s, then we can use it to apply to any pendulum. Now the last part, the third problem, that's when things get a little goofy. So I'm going to take periodic motion, and it'll just be moving this red pen back and forth in a straight line. But what I'm going to do is take a piece of paper and put it in the way. So if I keep going back and forth, I'll start to just draw a line back and forth. But what if I were to move this paper upward at a constant rate? What pattern would I see? I end up getting this wavy pattern. Now, it's not that good because I was trying to draw it on a paper floating in space, keep my hand steady, move the other one, but you get the idea. If I were to attach a pen to the bottom of any pendulum and pull a piece of paper along underneath it, I would get this wave pattern. This pattern, or this wave, can be a useful way of representing periodic motion. It's kind of a neat way to draw periodic motion. But when we draw this, we have some other pieces of information that we can look at. One of them, we use the symbol lambda, which is the Greek letter L to talk about. We use the symbol L to talk about length, and so do the Greeks. But in this wave, when we talk about length, we want to know how long it takes to go from one wave to the next. Just like we said, period says how long does it take to go from one repetition to the next. So what we'll do is draw a line right down the center, and I'm doing this backwards so I might mess up, and pick a couple points on this line. So here, and here, and here, we're at the same point. All right. Which of these represents a full wave? Here to here, or do I have to go the whole way across? Well, I'd like to be at the same place, going the same direction. And since I'm going up here and up here, we would say that this point, oh, this is weird doing it backwards, this point to this point would be one wavelength. Now if I pull this paper faster, so I'll go back to exactly what I was doing before, but move the paper really quick, look what happens to my wave. Well, if you can call that a wave. It gets really long. So wavelength has something to do with the speed at which this paper is moving past and the rate at which I'm drawing. Just like distance has something to do with, or displacement has something to do with the speed I'm moving and the time that I'm going to be traveling. We'll come back to this idea and talk about it in class, but hopefully this helps you get started with those problems. Bye.